Hello, in this video I'm going to look at the geometric series. So basically a geometric series is one of which that you have a sequence that has a common ratio. In either case, like for example, like if you have if you have a sequence, let's say that you have a sequence that's defined as maybe like um, a times r to the n minus 1, where let's say that a is equal to um, 3 halves, okay? And then let's say that the r is going to be 1 half, but raised to the n minus 1. Okay. Now, in this case, we have that this sequence converges because you have r is less than 1, basically. So the question, though, becomes what happens when we start adding the terms, for example. You have n equals 1 to infinity, and, this is 3 halves multiplied by 1 half raised to the n minus 1. Now, in either case, though, you could say that, for example, well, we learned that we could take the partial sum and then maybe look at the terms such that, to see if the sequence of partial sums converge, of which we'll see that they actually do. But here's where we have to kind of take a step back, that is, where we look at this sequence and we say, well, okay, sk would have to equal to n equals 1 to infinity, not infinity, but k, and you have a times r to the n minus 1. Expanding this, you'll have a plus ar plus ar squared, and then basically you have ar to the k, but it's minus 1, right? Now, if we multiply by r for sk, we'll have basically ar plus ar squared, and basically what's going to happen is that the last term is going to be ark. But notice that if you were to take the difference of the two, like if you were to take sk and subtract r times s sub k, this would basically just give you that you have a minus a, and then you have rk. Because basically, like, the idea is that if you make it negative, 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 that essentially you have that these terms begin to cancel out, these higher order terms, okay? And it leaves you essentially the first two terms, or the first term and the last term, that is. So how do we find sk? Well, notice that sk is 1 minus r multiplied, and that equals to basically a times 1 minus r to the k. How do you find sk? Sk is basically just going to be a times 1 minus rk, and then this is 1 minus r. Now note that we did say that, for convergence of the sequence, it has to be such that r is less than 1. Well, granted that that is the condition, that would imply that the rk, once you take the limit as k tends to infinity, that basically for this one you have a 1 minus rk, and all of this is divided by 1 minus r. But in either case, this equals to a over 1 minus r. Why? Because basically you have that the rk is tending towards 0. So essentially we have that the sequence, or series, n equals 1 to infinity of a times r to the n minus 1, it converges to 1, or a, over 1 minus r. But that's given that, the magnitude of that is less than 1. Okay, well, how does that help us? Well, it helps us in the sense that, if we considered the sequence that we were talking about earlier, you have that was n equals 1 to infinity, and that was 3 halves multiplied by 1 half raised to the n minus 1, and that this would be basically the first term, so that's going to be 3 halves divided by 1 minus 1 half, but in either case, this is going to be 3 halves over 1 half, which is equal to 3. So we have that essentially the value of which that this series converges to is 3. It doesn't necessarily, say that it's going to be 3, but it's going to approach it in actuality. But one thing that becomes interesting is, like for example, what if you had n equals 1, and this was to infinity, but you had something like, 2/3 raised to the n plus 2. Well, in this case, notice that, like if you were to expand it, what would that be? That would be basically 4/9 plus, well, the next term basically is going to be 2 to the 4th. We can rewrite that, right? Yeah, let's rewrite that. Why not? So this will be 2/3 raised to the second power, and this will be 2/3 raised to the third power. Okay, I don't know why. Hold on. Okay, yeah. So, actually, my powers were incorrect. Okay, so that's going to be 3, and then that's going to be 4, because it's n plus 2, right? Now, of course, this goes on forever, right? But check this out. What if I was to factor out the 2 to the third? Why? 2/3 raised to the third power. Why? Because it's the first term, is it not? 2/3 times 2 cubed, which multiplied by 1 plus basically 2/3 to the first power, plus, and the next term would be 2/3 raised to the second power. Now that means that this series is technically still, it's still geometric, and it's still in the proper format that we can work with, because basically you have that that's going to be 8 over 27 is going to be multiplied by now the reindex series as 2/3 raised to the n minus 1. But this is not too bad, because now you have 8/27ths, and this is going to be multiplied by 1 over 1 minus 2/3, which in either case is going to be 8 over 27, multiplied by 3 over 1, which in either case gives us 8 over 9. So that means that the series converges to 8/9. But in either case, like for something that, like if you had a series and it started at basically 1 and it goes to infinity, but notice that if you had 3 halves and it was raised to the n, this series diverges. This series diverges due to the fact that you have that the r is 3 halves, but that's greater than 1, which is enough to show that that series is not geometric and that it basically diverges. Similarly, if you were just looking at the convergence thereof of the geometric series, 2/3 is less than 1, so automatically we know that that's a geometric converging series. But then, like if it was negative, you would just have to make sure that the r is within, this parameter, which is basically like saying that r has to be between -1 and 1, not inclusive, that is. Otherwise, it would not converge in either case. Now, I would suggest that, when it comes to geometric series, that you do look at, for example, like what would occur if, for example, like you had a series and it started at a completely different index, and you have that, its ratio might be, like -1/3 but it's like raised to the, let's say like n, for example. Like, how would you re-index this so that you can show that this converges in either case? But I always say that it's more or less like bookkeeping, in terms of like figuring out the converging value. And then another possibility that you could have, for example, is, well, what if it was a finite geometric series sum? Like if you go from 1 to, let's say, like 99, and then your common ratio was, let's say, like 5/6, and it's raised to the, let's say, like, it's raised to the n. Like, can we figure out what this value converges to similarly? And the answer would be yes, but you would have to basically look at, like, what could you do if you had a geometric series and it goes from 1 to, let's say, like n, and you have that it's going to be a to the n, a times r to the n minus 1. And, think about that. Like, what would the sequence in this case look like? But if you revert back to the formula that we came up with for the partial sum, then in that case, that actually answers the question as to, like, what happens when you're trying to calculate, that is, a finite series sum that is geometric, that is. And, that's kind of interesting because in that case, that applies in real-world practical applications when we're talking about, like, paying off an annuity, whether it's a future value or whether it's a present value, which in either case is more or less relevant to, things of which that we have such things like compound interest and paying off an obligation, like a debt, or in any case, like some type of loan, for instance. So geometric series is actually very applicable to a real life scenario, which includes mathematics of finance.